So you should have gotten your exam back by email. If anybody did not get it, please let me know. Um, let's see. So I've got in this class 12 students, and okay, most of you are here today. It seems like we were mostly absent before, and the grades on the first exam. Now, I've taught this course, I mean, at least a dozen times. And the results on the first exam are usually better than what I got this time around. We need to be present and participating in the course. If you didn't do as well as you would have liked on the first exam, it's okay. I mean, we've got 4 exams and we've got 3 more midterms and a final. There's still a ways to go yet. And if you do better in subsequent exams, I'll take that into account. The other thing is I got the feeling like some people didn't scan they had a lot of missing problems. Like they didn't scan their exams fully. They missed a page scanning it or something like that. It's your responsibility to scan it and give it to me. So I'm not sure what I can tell you. Let's be present and let's participate together so we can learn. Because after all, that's why we're here. Okay. The second exam, I mean, not the results was that bad. I mean, I'm not trying to say to folks like the results were horrendous, but not as good as what I'm used to. Exam 2 will cover sections. So on the syllabus, if we could speak rather than using the chat, it's too hard to zip back and forth like this.
I didn't see my grade on Pilot.
Oh, I don't put them on Pilot. I just, use an Excel spreadsheet on my own machine and calculate the grades there. I mean, you've got I gave it to you. So, write it down. And, it's only going to be 5 grades, so it's not that much to keep track of. Where's what was I talking about? So the solutions for the exam right here. So the final exam is going to consist of, problems from, not the same problems, of course, but a selection of problems from exams 1 through 4. So, take a look at the solutions here and, correct your errors. And that way, like if, similar question to number 2 or number 1's in the final exam, then you'd be ready for it that next time around. Exam 2, so we'll be coming up sooner because we're not covering as much material here. So 4.1 and then 4.3 to 4.7. Okay. So I would say in 2 weeks maybe. So what's today? So tentatively the June 16th, we'll say. So tentatively covered for June 16, Wednesday. All right. So last time we were covering section 4.1. And we got to the last bit there, number 31. So we covered up to number 31, right here. And then we'll move on from there. So the next problem on the list is in 4.147. So number 47, so we have this function, z equals x squared plus y squared minus 2x minus y. Describe several contour lines for this two-variable function. So 4.1, number 47. So describe several contour lines or level curves for z equals x squared plus y squared minus 2x minus 2y. Okay, so you're going to be picking right, several values for c, and then, you know, seeing what those look like. So let us take c or z. So z equal to 0, say. This is 0 is equal to x squared plus y squared. Well, before we do that, let's rewrite this function. Let's rewrite the function first. So this is z equal to x squared minus 2x plus y squared minus 2y. And of course, we can complete, x squared. Complete the square with both of these. Plus y squared minus 2y plus 1, and then minus 1 to keep it the same. So z is equal to, so this is x minus 1 squared plus y minus 1 squared minus 2. Right? So, well, if we look at z equal to, say, minus 2, right, minus 2 is equal to x minus 1 squared plus y minus 1 squared minus 2. So 0 is equal to x minus 1 squared plus y minus 1 squared. So this is the circle of radius 0 centered at 1, 1. Right, so it's just this point here. And then if we took, say, z equal to minus 1, if you took z equal to minus 1, then you get, in the end here, when you put a minus 1 here and you have that minus 2 over there, so 1 is equal to x minus 1 squared plus y minus 1 squared. So this is the circle of radius 1 centered at the point 1, 1. better. So this is the contour z equals 0, z equals 1. And then the next one out, so that, you know, we get circles with integer radii. So z equal to 2. If you had z equal to 2, then, you know, when you go through this procedure again, you have 4 is equal to x minus 1 squared plus y minus 1 squared. So that is the circle of radius 2. That's better. Really hard to draw this on these tablet screens. They're very slippery. Oh, this was z equal to negative 1. This was z equal to negative 2, excuse me. Negative 2, negative 1, z equal to 2. Right, so, you know, you have these circles, right, for centered at 1, 1, for the contour lines or the level curves of the function. If you wanted to graph the whole thing, well, what is it? Then, you know, you might look at some of these other traces setting, say, x equal to 1. If you set x equal to 1, then you get z is equal to y minus 1 squared, like that. So in the y plane, you know, that's the parabola x equal to 1. So not in the xy plane. In the plane x equal to 1, which is right here, this is the parabola that bottoms out at 1, 1. So you have this parabola here parallel to the yz plane. And same thing, if you set y equal to 1, then you get the parabola going this way, and then you have those circles. And so you get this paraboloid, except instead of being centered at the origin, it's centered at this point 1, 1, 0. Okay? Any other interesting problems like that? Nothing off the top of my head seems to be calling out. Let's see what the next problem is going to tell us. 48, 49. Okay, so now in 48 and 49, we're on to level surfaces. So these are 3 variable functions. Okay, now remember, a 3 variable function, you can't really draw the graph of the 3 variable function. You can draw, right, you can draw the graph of a 1 variable function in 2 dimensions, 2 variable function in 3 dimensions, 3 variable function in 4 dimensions. But, you know, I mean, drawing in 4 dimensions is not so easy. Can be done, but, you know, not necessarily worth it. So in number, let's take 49 first. Find the level surface for c equal to 9. So you have w equal to x squared plus y squared plus z squared. All right, the level surface for w equal to 9 is 9 equals x squared plus y squared plus z squared, which is the sphere of radius 3, centered at the origin. Right, so you have the sphere centered at the origin. Let me do it. Of radius 3. So essentially, what that is telling us, so this is W equal to 3, or 9, with intersection points at x equal to 3, y equal to 3, z equal to 3. What that tells you is anywhere on this sphere for x, y, and z that lie on the sphere, right, x squared plus y squared plus z squared equals 9. Right, so the function takes the value of 9 on that sphere. Smaller spheres, W will take on smaller values. Larger spheres, W will take on larger values. 48. X minus 2y plus z. So level surface for W equal to, what was it, 4? Yeah. Level surface for W equal to 4. So this is 4 is equal to x minus 2y plus z. So what kind of surface is that? What's this? That's a what? Linear equation for x, y, and z.
Is it a plane?
That's a plane, right? X-intercept, how are you going to find the x-intercept? Put y, well, x-intercept is along the x-axis, which is where y and z are both what?
0.
0, right? So it's x equal to 4. And then on the y-axis, if you set x and z equal to 0, you're going to get y equal to negative 2. So half of that length. And for x and y equal to 0, you get z equal to 4. So that's well, that's kind of nasty looking. Now, these lines are too close. Let me just move this out just so we can see it better. All right, so there's that plane. Now, again, it's hard to draw a plane. I mean, I can draw a plane. So here's a plane. It's kind of slanted upward in some direction. But I mean, to get the right angle relative to the x, y, z axes is not really that easy. Okay, so one way to graph a plane is to look at just like how we graph a line in 2 dimensions. You find the x-intercept and y-intercept and just draw that line, connecting those. Or using any other 2 points. So here, we just find x, y, and z intercepts. It makes a triangle, and then the rest of the plane just is the extension of that triangle in all different directions. Alrighty. 50, 53, and 54. 50. Oh no, 50 is different. 50 is x squared plus y squared minus z squared. And describe the level surface for W equal to -4. Right, so this is -4 is equal to x squared plus y squared minus z squared. Okay, so this is a surface, right? Just like this is a surface and that is a surface. This is the surface along which this function w equals x squared plus y squared plus z squared equals 3. This plane is the surface for which this function w equal to x minus 2y plus z is equal to 4. Right? So on and so forth. You know, you can take different numbers and get different level surfaces. So here, what is this level surface along which the function w is equal to -4? Well, this one, right, if you let z be a constant, right, we've seen this type of surface already. Right, if you let z equal to k, right, then you get k squared minus 4 equals x squared plus y squared, and those are circles. Circles parallel to the xy plane. And then if you let, say, x equals 0, then you get z squared is equal to y squared plus 4. That's, x equal to 0. Oh, no, I did that wrong. X equal to 0, then you get minus 4 is equal to y squared minus z squared. And that is a hyperbola. Let's say x equal to 0 minus 4 equals y squared minus z squared. That's a hyperbola. So 4 is equal to z squared minus y squared. So that's a hyperbola in the yz plane that opens up in the z direction along the z-axis. Right, so you have circles, circles parallel to the xy plane, and then you have these hyperbolas in these directions opening up along the z-axis in the yz plane. Same thing in the xz plane. If you were to work that out, and so here are those circles. Right, so you've got this hyperboloid of two sheets here. The downward facing one, this axis is in the way. Let me get it out of there. There we go. So this is the level surface for w equal to -4. Where does this happen? This is at 2 and -2, where that z-intercept happens. All right, so the function w takes on constant values along these hyperboloids of two sheets. This is the one along which it's equal to -4. '53, '54. Well, find an equation of the level curve of f that contains the point P. Oh, okay, this is nice. So 53, fxy is 1 minus 4x squared minus y squared. All right, so which level curve contains the point 1, 2, was it? Contain, no, 0, 1. Right, well, all you do is you see, well, what is the value of f or z, or whatever, however you want to denote the function. What is the value of f or z at 0, 1? Well, that is 0, right? So f of 0, 1 is 1 minus 4 minus 1, which is 0. So 0 equals 1 minus 4x squared minus y squared contains 0, 1. And what is that function here? Well, that's just the ellipse whose radius in the y direction, along the y-axis, is 1, and along the x-axis, right, so this is, let me redraw that, 4x squared minus y squared equals 1. So this is x squared minus y over 4 equals, and it's already equal to 1, I'm sorry. So x squared over 1/4 plus y squared equals 1. So you have radius in the x direction of half radius in the y direction as 1. So there's the point 0, 1, and here is the level curve for f of xy equal to 0. Or was it 0 or 1? 0, 1, yeah, equal to 0. And then 54. Just the equation, so the level curve that contains the point x equal to 1, y equal to 2, right, so this is f of 2, 1 is equal to, or 1, 2. So this is 4 times arctangent of 1, which is pi over 4. So that's just pi. So pi equals y squared arctan x contains the point 1, 2. Okay. So that level curve, and I'm not going to graph that, but I mean, it's the one that does contain that point. All right, moving on to 4.3. We've finally made it to the partial derivative. All right, so 4.3, number 114. So for the following exercises, calculate the sign of the partial derivative using the graph of this surface. So for that, two variable function. So what I'm going to do, open image in new tab, copy image. Let us stick the image right there. So, how many of these problems are we doing here? Well, let's just do 114 to 117. Yeah, just 114 to 117. So, a partial derivative with respect to x of 1, 1. So, here's the x. So, pay attention where the x and y axes are. So, the x-axis is in this direction, and here's 0 on the x-axis. Here's 0 on the y-axis. So, the origin is, right where that guy is bottoming out. That's 0, 0. Right, so this is the x-axis kind of like moved off of where it usually is. So the x-axis is right there. That's the x-axis. Positive x-axis. Whoops. Okay, it's not going to let me do that. Here's the positive x-axis right here. I know it doesn't look that way, and this is the positive y-axis, right? Or that's the negative y-axis, isn't it? That's the positive y-axis right there. All right, y equal to 0, y equal to 1, y equal to 2, and that's the origin right underneath there. Okay, f partial derivative with respect to x at 1, 1. So 1, 1 is right here. So what color shall we use? I think blue. So here is 1, 1. All right, there's 1, 1. So f of 1, 1, actually these lines are just going to be, let's try this again. It's just awful looking. All right, so here's 1, 1. 1, 1 is right here. 1, 1, 0. So 1, 1, z is right there. All right, so that's x equal to 1, y equal to 1, z equal to, whatever that z value is off of the xy plane. The partial derivative of f with respect to x is the slope of the line in that, tangent to that surface in the direction of the x-axis. The direction of the x-axis is that way. All right. Right, that's the x direction. Right, so the slope of this surface in that direction is what? That's the positive x direction. So the slope of that surface in that direction is what? Here's that direction, x direction. Right, lift this line up to the surface. Right, so this line is in some vertical plane. Right, here's the vertical plane that line is in. Right, lift that vertical line up to the surface till it's tangent. Keep it straight, but lift it till it's tangent. Pointing up or pointing down in the z direction? Is z increasing or is z decreasing? Is it pointing up or pointing down? Well, it's right there. Right? That tangent slope. Is that the increasing or decreasing direction for z? Guys? All right, that's the positive x direction. You lift that positive x direction to a tangent line to the surface, lift it straight up, and you get a line that's sloping upward, so it's positive. 115, fx of negative 1, 1. Negative 1, 1 is right there. So x equal to negative 1, y equal to 1. And then again, we're looking in that x direction. So here the tangent is going to be like that. Positive or negative? Are we going, so when we're moving in the positive x direction, are we going up or down? We're going down. So it's negative. Right? While you're moving in the positive x direction, z is increasing at this point. Here, when you're moving in the positive x direction, z is decreasing. Fy11 right, so the positive y direction at that 1, 1 point is, let's do a different color here. Orange isn't good. Green is good, I think. So going in the y direction, right, which is like that, that's the y direction, and that is a horrible line I drew. So there's the positive y direction, this way. You lift that up to a tangent line in that plane, and you get that. And in this case, as y moves in the increasing direction, z is going down. So that's negative. And then f, partial derivative of f with respect to y of, partial fx 0, 0. Well, at the origin, which is right there, this is where the curve of that surface is bottoming out. So this is neither positive nor negative, it's 0. And so this was 114 to 117. $118. For the following exercises, calculate the partial derivative for z equal to cosine 3x cosine 3y. So this is the function z equal to fxy. Calculate the partial derivative of z with respect to x. Okay, so when calculating the partial derivative of z with respect to x, you hold y to be a constant. Okay, we're calculating the rate of change of x in the f direction, the rate of change of z in the x direction. Right? We're not considering the y direction at all. So you just hold y to be constant. Right? So holding y constant, right, gives me that cosine 3y is just a constant. So the derivative of this is what? The derivative with respect to x when y is held as a constant. When y is held as constant, this whole thing is a constant. So what's the derivative of the sine 3x? Well, that's 3 sine 3x cosine 3x times the constant cosine 3y. So there it is. 3 sine 3x times cosine. Wait a minute, what did I do? Three sine 3x. That's it. Times the cosine 3y, which is a constant. So that's the partial derivative of z with respect to x. We're just taking the derivative of that part, because that's the variable part. This part is constant. So this derivative with respect to x is 3 cosine 3x. Derivative of sine is cosine. 3 cosine 3x times 3 for the chain rule. And then the cosine 3y is constant. $122 calculate the partial derivative. So fxy is e to the xy cosine x sine y. And calculate the partial derivative with respect to y. Right, well here x is held constant. So it's cosine x. What number is that? 122 cosine x sine y. So here the x is a constant and y is the variable. So this cosine x is constant as well. So this is just a product of two functions of y, e to the xy, sine y. So you use the product rule. First, the derivative of e to the xy, okay, with respect to y. So that's e to the xy times x. So x e to the xy times the second sine y, and then cosine x, because that constant is still there. And then e to the xy times the derivative of sine, which is cosine of y, times that constant cosine of x. Okay. E to the xy. Why did I write it like that? E to the xy sine y, cosine y, and then times cosine x. So you could rewrite this as e to the x cosine. Well, it's got a cosine x in it as well. E to the x cosine x. E to the xy cosine x. So that's x sine y plus cosine y. Now, by the way, since you've got the derivative with respect to x, the partial derivative with respect to x, one could also calculate the partial derivative the partial derivative with respect to y. One could also calculate partial derivative with respect to x, right? So here the sine y is constant and the x is variable. So this is y e to the xy. Y e to the xy cosine x sine y plus e to the xy cosine x derivative is minus sine x sine y. So this is e to the xy sine y times y cosine x, or y cosine y, no, that's cosine x, y cosine x minus the sine y's factor out, sine x. All right, so we have the partial derivative with respect to y and the partial derivative with respect to x. All right, next is 124. Let z be natural log x over y. Find, so it's both first partial derivatives, partial z with respect to x and partial z with respect to y. Okay, so that's again the differential notation, and then of course you also have this. This is the notation that takes the place of priming, right? In the past you had f of x and its derivative was f prime of x, but you also had f of x and its derivative, in differential notation, df dx. In general, the differential notation is a little more informative than the other, but it's not always, strictly speaking, necessary. So here, partial derivative of z with respect to x. Well, first of all, z is natural log x divided by y. So this is the natural log of x minus natural log of y. Right? The log of a quotient is the difference of the logs. So partial z with respect to y, well, this one is 0. And that's minus 1 over y. And partial z with respect to x, well, this one is 0 because y is a constant. And this one is just 1 over x. One 128. So fxy is xy over x minus y. Right, and we want to find partial derivatives at special points. Oops, I'm doing 128. Partial fx, f with partial derivative of f with respect to x at 2, negative 2, and same with y. All right, so find the partial derivative with respect to x, and then at the point 2, negative 2, what exactly is the value of that partial derivative? Same thing with partial derivative with respect to y. Okay, so partial derivative of f with respect to x, okay, just in terms of x and y. Normally we skip like putting in those things, just call it f, because otherwise you just spend too long just writing out the function. Just the functional notation. So normally, maybe we just write that, but I'll be more specific here. Partial derivative of f with respect to x. So I've got to use the quotient rule here, right? So derivative of the top with respect to x, well, y is a constant, so it's just constant times x. So the derivative of the top with respect to x is y, minus the derivative of the bottom, f with respect to x, is just 1. Right, the partial derivative of this with respect to x. Partial derivative of x is 1. And the partial derivative of the y, it's a constant, is 0. Because we're taking the partial with respect to x. So partial derivative of the bottom, which is 1 times the top, just xy, over the bottom squared. Right, so I don't think this has any simplifications. Right, f prime x minus, sorry, derivative of the top times the bottom minus derivative of the bottom times the top all over the bottom squared. Yeah, that's just about it. Something's not right here. Derivative of the top times the bottom. The derivative of the top times the bottom minus the derivative of the bottom times the top. That's what it is. So this is yx minus y squared minus xy over x minus y squared. So these cancel, and I'm just left with minus y squared over x minus y quantity squared. So that's the partial derivative of f with respect to x and y. So the partial derivative of f with respect to 2 and minus 2, or at 2 and minus 2, you just plug those numbers into here. So this is minus 4, and then x is 2. This is minus 2, so you add, you get 4, so that's 16. So minus a quarter. So that's the slope of the surface in the x direction at the point 2, negative 2. Negative slope of 1/4. Same thing with y. Partial derivative of f with respect to y at just xy. So here y is variable, x is constant. So the derivative of the top is just the constant times y. So the derivative of the top with respect to y is just that constant. So it's the derivative of the top times the bottom. Minus the derivative of the bottom. So the derivative of the bottom is negative 1 times the top. All over the bottom squared. So this is x squared minus xy plus xy over x minus y squared. So those go away, and I'm left with x squared over x minus y quantity squared. So partial of f with respect to y at 2 minus 2. So 2 squared is 4. On the bottom, oh, that's got a negative right there. X minus y, so again, 2 minus 2 is 2 plus 2 is 4, so 16, so just positive 1/4 here. Okay. Hey guys, let's take a few minutes break and come back. Let me pause this, restart this. All right, so that was problem number 128, problem 132. Find the area of a parallelogram with adjacent side lengths that are AB, in which the angle between these two sides, theta, is given by the function, not to find the area of a parallelogram with two adjacent sides of length A and B, and angle theta between those two sides is given by that formula. So we've seen that already, right? So you've got the parallelogram. So it's area in terms of A, B, and theta. This is AB sine theta. So that's the area of this parallelogram, right? That's the the length of the cross product. All right, so that's A, that's B, and that's theta. So this length here is A, this length here is B. And this angle over here is theta as well. Find the rate of change of area of the parallelogram with respect to side A, side B, angle theta. Right, so the rate of change of area as A increases, the rate of change of area as B increases, and the rate of change of area as theta increases, right? So this is the partial derivative of capital A. I guess maybe we should call it capital F. So area equals capital F. So they're asking you to find all those rates of change. So this is the partial derivative of F with respect to A. Right, so I have these wrong, don't I? This is B and this is A. Partial derivative of F with respect to A. So in this case, A is the variable, and then B and theta are constants, right? So the partial derivative of a 3-variable function defined the same way as it is with a 2-variable function. Right, just you have one more variable to do it with. So you let A vary, and you let B and theta be constant, and you just take the derivative as you did before. So this whole expression here, b sine theta, that's just a constant. So the derivative is just b sine theta. Right? It's just right. A is the variable, and that's just a constant. So it's just the derivative of k times a, which is just k. Same thing with partial derivative of f with respect to b. That's going to be a sine theta. Partial derivative of f with respect to theta, a little bit different. What's that one going to be? So a and b are constant. Theta is the variable. So what's this one going to be? Right, a and b are constant. So theta is the variable. Derivative of sine theta is just cosine theta. So in this case, partial derivative of f with respect to theta is what?
It's just A and B cosine theta.
Yeah. All right, so rate of change with respect to A, with respect to B, and with respect to C. 135. By the way, so in this problem, this is kind of nice because later, if you remember back from Calc 1, back in Calc 1, you studied these things called related rates, right? You had all these different related variables that were related. So A was a function with respect to time, B is a function with respect to time, theta is a function with respect to time. So you have these three functions, A of t, B of t, theta of t, all varying with respect to time. And then you get this relationship between them, like the area of this thing is supposed to be 4 or something like that. Right? And then find the rate of change of A when B and theta are equal to the certain, these problems, these related rates problems. But they were really complicated when you did them with one variable with single variable calculus. They were complicated because you had to use this not that complicated. You had to use this implicit differentiation. Okay, but now we don't have this just yet. We'll do it in section 4.5 with the chain rule. Those related rates problems become something very natural, and you'll see how that goes. So you'll see it in 4.5, and you'll think to yourself, "Oh man, why did I think it was so hard back then? It's so easy now." So that's one of the powers of multivariable over single variable calculus. All right, so 135. Z is natural log x minus y. And find f, partial derivative of f with respect to x, and then with respect to y. So these are higher order partial derivatives. Let's do a little bit more here. Okay. So let's find all first and second partial derivatives. So let's find all first and second partial derivatives. All right, the first partial derivatives are partial derivative of z with respect to x. So, this z sub x, or, you can write it this way if you want. All right, so partial derivative of z with respect to x, partial derivative of z with respect to y. Those are the firsts. And then the second partial derivatives are partial derivative of z with respect to x, and then with respect to x again. Partial derivative of z with respect to y, and then with respect to y again. And then partial derivative of z with respect to x, and then y. And then z with respect to y, and then with respect to x after that. But by Clairaut's theorem, these should be the same. For functions with continuous partial derivatives. Which these things are. Logs are continuous and polynomials are continuous, and you're just working with continuous functions and putting them together. I mean, log is continuous wherever it's defined. Of course, it's not defined in certain places, right? Like for negative arguments. And this was Clairaut's theorem. We don't actually prove Clairaut's theorem. That requires something a little bit more than what we do in this class. But we'll just take it as granted. It's fine. Okay, so let's find in order to find zxy, you're going to have to find the first partial anyway, zx or zy. But let's do all of them, right? So partial derivative of z with respect to x. So this is natural log x minus constant. So it's just 1 over x minus the constant. Partial derivative of z with respect to y. So now it's constant minus y. Now remember the derivative with respect to x of the natural log of g of x, right? It's this g prime of x over g of x by the chain rule, right? Maybe you think of it as 1 over g of x times g prime of x. That's fine, but this is more sort of a shorthand way of doing it. So that's just a derivative to remember. The derivative of the log of g prime over g. So here, right, y is the variable and it's negated. So minus 1 over x minus y, right? Zxx, so partial derivative of this with respect to x, again, this is x minus y to the negative 1, right? So negative x minus y to the negative 2. So that's minus 1 over x minus y squared. Zyy, same kind of thing here, right? Well, let's rewrite this. Negative x minus y to the negative 1. So it's negative, right? Negative the negative is positive. So x minus y to the negative 2 times the derivative inside, which is negative 1. So again, it's minus 1 over x minus y squared. So you notice that that's not standard. That's going to happen. The zxx is equal to zyy. This is just some weird function that it just happens to be true. Okay, I forgot what these types of functions were called. A function is called harmonic when zxx plus zyy is 0. This one is zxx minus zyy is 0, and that type of function's got a name too. I forgot what it's called, but anyway, so these are special functions. So you get this notion of partial derivatives, by the way, and then you can start making equations with, these partial derivatives. And such an equation is what? What do you call such an equation? What do you call such a thing? This type of equation. Equation in derivatives of z. Well, if it wasn't partial derivatives, it was just ordinary derivatives, what would you call it? Really? Are you all there? Are you all sleeping? Or what's the story here? It's called a differential equation, right? A differential equation is an equation in function and its variables. So f, f prime, f double prime, right? And then you take this whole course in differential equations if you're an engineer or a mathematician, or if you want to do chemical reaction analysis or something like that. This type of thing is a differential equation with partial derivatives called partial differential equation. Partial differential equations are really, really applicable. I mean, there's all kinds of very important physical type equations that are partial differential equations, wave equation, heat equation, all different kinds of things like that. And then you just have these simple ones like that, these harmonic equations. But you can hardly ever solve them. Right? So ordinary differential equations, you can hardly ever solve those, but the partials are worse. But you can still say things that are intelligent about it. Anyway, we're not done yet. So this is the first partial. This is the second partial, zxx, zyy. There's also zxy, so the derivative of this with respect to y. So that's going to be, right, so this is x minus y to the minus 1. So it's minus x minus y to the negative 2 times the derivative of the inside is negative 1. So that's 1 over x minus y squared. All right, so that's zxx, that's zyy, zxy, and then just for kicks, let's do zyx. So this is negative x minus y to the negative 1, so the derivative is negative times the negative is positive x minus y to the negative 2. Derivative of the inside is just 1. So it's 1 over x minus y squared. Right, and these are the same. As they should be. You only have to calculate it one way because you know it's going to be the same. So, you can do partial derivatives in any order. X first, then y, or y first, then x, as long as everything's continuous. Which pretty much all the functions we deal with are. That was 135. 138. So z is e to the x tangent y, another two-variable function. Find these. So this is zxy, zyx, and this should be the same. So find the partial derivative of z and Right, so this is the differential notation with partial derivatives, right? Remember, right, how differential notation works. So differential notation, let's do a quick review. It stands to talk about again. It's an important notation, right? Given, right, single variable y equals f of x, right? The differential operator d over dx the differential operator d over dx times y is equal to dy dx, right? And that's the first derivative. Right? The derivative with respect to x of y, and we use this multiplicative notation, is dy dx. And then the derivative with respect to x of the first derivative, dy dx, is, well, you just use this multiplicative notation, d squared y over dx squared. Right? That's the second derivative. And you can have the third derivative, fourth derivative, so on and so forth, right? D over dx times d squared y over dx squared, that's the second derivative. And you multiply these things together, it's d to the third y over dx to the third, and that's the third derivative. Let me draw this. First derivative. Second derivative. Third derivative, etc. Right, so now with partial derivatives, you just have more differential operators, and you don't use d anymore. You use this. It's a del. It's not even a Greek letter. It's just this thing people call del. For partial derivatives, you just have more differential operators. Instead of just del x, you have del x and del y. Right? And del z, if you have a three variable function, you know, whatever the case might be. All right, so this, you've applied partial derivative with respect to y first, and then partial derivative with respect to x second. You've applied two differential operators. So, right, for two variable function, fz equals fxy, like that. Now you have differential operators partial with respect to x, partial with respect to y, like that. So, right, like partial squared z, partial x, partial y means z, y first, then x. Yeah, first y. First y, then x. No, it goes backwards. That's nasty. All right, I never realized that. It's read from right to left. Right, because it means this. Means, right, partial with respect to x, partial with respect to y, z. So that's z, partial with respect to y coming first, and then x, because the multiplication is, closer multiplication is done first. All right, and d squared z over dy squared, that means you've applied the differential operator del over del y twice. Right, means z y y. Okay, so sometimes that differential operator notation is preferable to this subscript type notation. It makes certain properties more obvious. So, sometimes we use one notation, sometimes we use the other. It looks complicated when you first look at it. I mean, you look at it like, what is all that? But it's, once you know what it means, it's not that bad. All right, so here they're telling us, right, this is zyx, this is zxy, reading them backwards. All right, or forwards if you're reading in Arabic. So they should be the same, right? So first we'll find those first partials. All right, zx. All right, so e to the x is a function, tangent y is just a constant. So you just get that. Zy is going to be, tangent y is a function, e to the x is a constant. E to the x and the derivative of tangent is secant squared y. So zxy is going to be equal to, so that's the first partials, these are the second partials. Zxy, well, this is the same as z, so that's going to be e to the x secant squared y. And zyx is going to be, well, I mean, e to the x, derivative is e to the x, and secant squared y is just a constant. Right, so they're the same, as they should be. All right, so a little bit extra we can do. All right, let's find the other second partials. So the other second partials are zxx and zyy. You'll notice that zxx is just, this is function z again, e to the x tangent y. And then zyy is more complicated. So e to the x secant squared y, e to the x is constant. And then using the chain rule here, 2 secant y times the derivative of secant y is secant y tangent y. So zyy is e to the x 2 e to the x secant squared y tangent y. Right, so there's there's 4 second partial derivatives. 2 of them are the same when you have continuous first partial derivatives, which you do here, because tangent and e to the x are continuous. And e to the x and secant are continuous, as long as you're defined. I mean, you're not hitting any of those asymptotes that these functions have. So, Clairaut's theorem will hold, as long as we're staying on a domain where we are continuous. So symbolically, you would expect it to hold, and it does. So there's 4 second partials. 2 of them are almost always equal. And then there's 2 first partials, because you only have 2 variables. For 3 variable functions, you have more, of course. What number was that? That was 138. 143. So here's three variable functions. So f x, y, z is x squared. Oh my goodness, really? X squared y to the third z. Just write f for the function. You don't need to write f of x, y, z. X squared y to the third z minus 3x y squared z to the third plus 5x squared z minus y to the third z. Hopefully I copied that right. X, Y, Z, X, Y, Z, X, Z, Y, Z. So 2, 3, 1, 1, 2, 3. 2, 3, 1, 1, 2, 3. 2, 1, 3, 1. 2, 1, 3, 1. 1, negative 3, 5, negative 1. 1, negative 3, 5, negative 1. Great. So find partial derivative with respect to x, and then y, and then z. Right, which is going to be equal to partial derivative with respect to y, and then x, and then z, which is going to be equal to the partial derivative of z, y, and then x, partial derivative of z, x, and then y. They're all going to be the same because you can do them in any order, and there's 6 of them. There's 6 permutations, 3 factorial permutations of 3 symbols, and this is a polynomial, which is the ultimate continuous function. It's always continuous everywhere. I guess I shouldn't say that. Sine and cosine are the ultimate continuous functions. And e to the x. So do them in whatever order you want. Partial derivative of f with respect to x. So this is 2x y to the third z. Right? Because the y to the third z is a constant. So you just, x squared is 2x. Minus 3 y squared z to the third. Plus 10 xz minus 0. Right? There's no x here. Y to the third z is a constant with respect to x. And then partial derivative of this with respect to y. So this is 6x y squared z. Right? You just, the derivative of y to the third is 3y squared. And then the x and z are just constants. Here, 6yz to the third. xz, no y's there, so that's all just constants, so the derivative is 0. And then partial of this with respect to z, and you get 6xy squared minus 18yz squared. That's your final answer right there. Hopefully I got that right. Let's take a look. 143. Six y squared x. Where'd you go? 6y squared x minus 18yz squared. Yeah, that's right. All right. 145, 149. So at 145, oh, this is that harmonic partial differential equation. Anyway, so this is what we're going to talk about later in section 4.6, 4.7. So, which one was it again? 145. fxy is x squared plus x minus 3xy. f is equal to x squared plus x minus 3xy plus y to the third minus 5. So find all points x, y for which partial with respect to x is equal to the partial with respect to y is equal to 0. So with a single variable function, right, this was where, the slope was 0. Right, so with a single variable function, right, you could have a local maximum, local minimum, or neither nor, like you'd have these saddle points. Right, where the tangents were horizontal. With two variable functions, you get similar sort of thing. You can have local maxes and mins, like that. So partial derivative in the x direction or that's the y direction and z direction are both horizontal. So you have relative maxes, relative mins, and you also have these saddle points like that hyperbolic saddle thing, right, which has derivatives, horizontal derivatives in both directions. So these are important things. I mean, dealing with optimization, finding maximums and minimums of functions. Right, so we'll do that later. So, but here, partial derivative of f with respect to x is 2x plus 1 minus 3y, and then that's 0. And we'll set this equal to 0. And partial derivative of f with respect to y is equal to minus 3x plus 3y squared, and these derivatives are 0. So, and set this equal to 0. So let's see. So this says what? This one says that x is equal to y squared. Right? This one says x is equal to y squared. So then I go to the first equation, and I get 2y squared plus 1 minus 3y is 0. So 2y squared minus 3y plus 1 equals 0. So this is 2y minus 1, y minus 1 is 0. So y is a half or 1. So y coordinates of the points where both partial derivatives are simultaneously 0 are at 1/2 and 1. So now you find the x's by, just checking each one of these. So when y is equal to 1, you get 3x is equal to 3. So that's x equal to 1. And in this equation, 2x plus 1 is equal to 3. So you take y equal to 1 and you plug it into both equations. Right? Take y equal to 1, you plug it into both equations. This equation gives you x equal to 1. Right? This equation gives you 2x plus 1 equals 3. So 2x is equal to 2, so x is equal to 1. Good. So both of these worked. Right? It could be that one equation works and the other one doesn't. One equation gives you one solution for x, the other equation gives you a different solution for x, in which case it doesn't work out. There is no point with y equal to 1 for which xy is equal to 0. But here, we got the same. Right, so at 1, 1, So at 1, 1, fx equals fy equals 0. So that's called a critical point, just like it is with single variable functions. So that's when y is equal to 1. When y is equal to a half, I plug this into here, and it says x is equal to 1/4. Right? When I plug y equal to a half in here, I get 2x plus 1 is 3/2. So 2x is equal to 1/2. So x is 1/4 again, right? So these are the same. At xy equal to 1/4, comma 1/2, fx equals fy is equal to 0, both. Again, a so-called critical point. So we'll do more of those sorts of things in section 4.7. So this function has 2 critical points. So 2 points where you can get relative maximums and minimums. Where you might get, you could have a hump up or a hump down, or you could have these funny saddle points. There's all kind of funny saddle points that you can get. And the question is which is which. It's not quite so easy to tell with multivariable functions, although you can often tell. And some types of questions you don't actually need to know, but we'll talk about that later. 149, e to the x sine y, show that z equal e to the x sine y satisfies this. In other words, it's a solution to this equation, partial differential equation. So show that e to the x is a solution to the partial differential equation zxx plus zyy equals 0, the harmonic equation. Okay, so just check those variables, those partial derivatives. So zx is, well, it's e to the x sine y. So zxx is, again, e to the x sine y. Zy is equal to e to the x cosine y. And zyy, well, derivative of cosine is negative sine. So negative e to the x sine y. And throughout that process, the e to the x was constant, right? So we see zxx plus zyy is equal to e to the x sine y minus e to the x sine y is equal to 0. Right? So it's a solution to that partial differential equation. And then, one type of question that people ask is, with partial differential equations, it's not like, here's partial differential equation, find all the solutions for me. Like, sometimes with ordinary differential equations, you know how to do that, like with these linear differential or linear second order or even third order linear differential equations, ordinary differential equations, homogeneous. And you can find those solutions, all of them. So another sort of weaker problem that you can ask is, well, okay, here's a solution to the harmonic equation, right? Can you find all the sort of variations of this? So can I put a constant k next to the x? Can I put a constant a out front? Certainly I can put like 3 e to the x sine y. So like, how can you generalize that function to get more solutions? Right? Not that you necessarily want to find all solutions. What you'd like to, but it's too hard sometimes. I love math, can you tell? You guys do too, but you're holding back. You're holding the love back. Let the love flow. Speak, participate. All right, the law of cosines can be thought of as a function of three variables, right? So f, x, y, theta, x squared plus y squared equals 2xy cosine theta, gives this square of this third side of the triangle. Find df d theta df dx when x is 2, y is 3, theta is pi over 6. So they're kind of warming you up for these related rates problems here. Right, so, right, you've got this angle theta here. So this is x, this is y, this is f, right? Or, no, I'm sorry. This is z. All right, so the law of cosines is that z squared is equal to x squared plus y squared minus 2xy cosine of theta. Right, of course, that's where this connection with dot products and angles comes into play. It's from law of cosines. So now you just got this function f x squared plus y squared minus 2xy cosine of theta. And now they're asking you just find the partial derivatives df d theta and df dx when x is 2, 3, pi over 6. So find and with the differential notation, you use this kind of like with the ordinary subscript notation, you would do this 2, 3, pi over 6. Find the partial derivative f with respect to x at 2, 3, pi over 6. With the like the differential notation in a single variable, we used to go like that. Find dy dx at x equal to 5. So here, find df dx at xyz or xy theta equal to 2, 3, pi over 6. Okay, it's definitely a sloppier notation than this or this, but it's okay. It's not that bad. I've seen worse. And then df d theta for 2, 3, pi over 6. So first you have to do just f, just find df. So this using that differential notation. Find df dx. Derivative here is 2x. Derivative of y squared with respect to x is 0 minus 2y cosine theta. Right? So partial f partial x with respect, so at 2, 3 pi over 6 is equal to, so 4 minus 6 cosine pi over 6, which is root 3 over 2, is 4 minus 6 root 3 over 2, so that's just 3 root 3. All right, so that's the partial with respect to f at partial of f with respect to x at 2, 3 pi over 6. Partial f with respect to theta, well, the derivative of this term and this term, there's 0. The derivative of that one is derivative of cosine is negative sine, so it's just 2xy sine theta. So partial of f with respect to theta at 2, 3, 6 is 2 times 2 times 3 is 12, or not 6, pi over 6. 12 sine pi over 6, which is a half, so you just get 6. Okay. That's the last problem in that section, eh? 159. Yeah. So, moving on to, so that's just the basic mechanics of and meanings of partial derivatives. In this next section, we start looking at the geometric properties of these partial derivatives. In the tangent plane, with the interpretation in terms of tangent planes. So instead of tangent lines, right now we've got these tangent planes. So section 4.4, number 167. So let's remember that picture. See if I can find it. I'll just pull it off the web page. Section 4.4. Right. So, I thought I had a nicer picture than that one. I guess it was that bad, huh? Let's see. Function on screen. Whoops. That didn't work. Oh, I pushed the wrong button. Here we go. No. Go away. Do I just push that? No, I guess so. Right, so remember this tangent plane notion. Okay, you've got the function's surface z equals, or the graph of the function z equals fxy. At point AB, the slope in the x direction is the partial derivative with respect to x at AB. And in the y direction is the partial derivative with respect to z at, or it shouldn't be a y. It should be a y. Partial derivative with respect to y at AB. Right, so I have this line and this line are both tangent to that surface. The two lines together form a plane. Right, they don't form a plane. They define a plane. Right, and that's the tangent plane. It's the plane that touches the surface locally at just that point. I mean, of course, not locally, like further away from that point, it can intersect the surface all over the place, but it doesn't matter. In a small neighborhood around that point, that plane just touches the surface at that point of tangency. Same idea as a tangent line. And the equation, right, for the tangent plane was z minus FAB equals partial with respect to x at AB, x minus A, plus partial with respect to y at AB y minus b. Right? And it's just a, right? It's just like y minus f of a is equal to f prime of a x minus a. Right? It's just like that. That was the single variable tangent line. Right? If you just look at the point, if you set y equal to b as a constant on this plane, then what do you get? If I just set y equal to b, then on this blue line, I'm at this red point, and what I'm going to get is that orange line. And that orange line is essentially a tangent line to the function just at y equal to b. So the function parallel to the function when you cut it on the plane y equals b. You get this curve, and that's the tangent line. And that's the equation of that tangent line. Z minus point of tangency equals derivative f prime times x minus a. Okay, although things are a little more complicated, it's partial with respect to x at ab instead of just f prime of a. Right? And then similarly, if you let x equal a, then you get this tangent line in the y direction. So the plane is just, sort of the amalgamation of those two equations there. And, now that we've got the equation for that tangent plane, now you got an equation for a normal vector for free, right? Because the plane gives you, it's just the coefficients of x, y, and z. As long as you put them all in the same, you got to rearrange terms, but, it gives you now a normal vector. You've got a normal vector. It's partial f with respect to x, partial f with respect to y, and then negative 1. Okay. So 167. What's the deal? Oh, next section. $167. So for the following exercises as a useful review, find the normal vector and tangent vector at point P. So we'll find the normal vector and tangent vector. So the normal vector and a tangent vector would be given by the plane itself. I'm not sure what they mean by that. Oh wait, this is in 2-dimension. Oh, this is in 167. This is in 2 dimensions. So xy squared minus 2x. So this is a whole different problem here. Should we spend time on this? I'm not sure. Plus y. Let's not spend time on that. It's not necessary. That's 167, 169, 172. So let's leave out those first. So 167, 169, just omit those. All right, so 172. So we've got the surface x squared plus 10xyz plus y squared plus 8z squared. Equals 0. So this equation gives you a surface. It's not a function z equal to fxy just yet, okay, but, we can make it so. So find the equation of the plane tangent to this surface, the surface given by this equation, at point minus 1, minus 1, minus 1. And if you plug in minus 1, minus 1, minus 1, this is 1 plus 8 is 10. Plus 10 times minus minus minus, so it's minus 10. So that's equal to 0. So it's on that surface. Solve for z in terms of x and y. So with this one, you cannot solve for z in terms of x and y. So what are they driving at here? Hint, solve for z in terms of x and y, but you can't solve for z in terms of x and y. So what do they mean? You can find partial derivatives using implicit differentiation, but we don't want to do that right off the bat. So this is the problem with this book, is they say things and the problem is not correct. So you cannot solve for z here. What we could do is modify this a little bit. If I get rid of this z right here, then we can. Although I got to change that point as well. So 172 is not solvable in the way that they're saying. Modified to be solvable. So we're going to have to make the y a positive 1. And the z a positive 1. So now it will work. And we'll get rid of that z here. So they're saying to solve for z, but you cannot solve for z because that z was there. Now we can do it. Okay, so let's solve for z. So 8z squared is equal to minus x squared minus 10xy minus y squared. Divide by 8. It's still a big mess. And then take a square root. Oh, I mean, that's just awful. That's just awful. It's 170, 174. All right. 172 is just I mean, I don't know what they're getting at, what they want you to do exactly. but it's not solvable in the way they want you to do it. I mean, there are things later that we can do. We can find the normal vector to the surface at that point. And once you have the normal vector to the surface at that point, you can find the plane, no problem. You know, just using that equation. But here you just can't. Oh, 172. That's just, you're gonna have to omit it. We'll add some other ones on. Uh, 174. So 174, z equals e to the 7x squared plus 4y squared. So find the equation of tangent plane at 0, 0, 1. Right, so so you need those first partial derivatives, z with respect to x and z with respect to y. So partial derivative of z with respect to x is equal to, well, it's e to that function times the derivative of the inside, which is 14x e to the 7x squared plus 4y squared. Z with respect to y, 8y e to the 7x squared plus 4y squared. And partial of z with respect to x at 0, 0 is 0. And the partial derivative of z with respect to y at 0, 0 is 0. So it's a horizontal tangent plane. So using this equation here, z minus f of ab, that's the 1, is equal to, well, this is 0 times x minus 0 plus 0 times y minus 0. So you just get the horizontal plane z equal to 1. Very exciting. 176. X squared plus 4y squared equals z squared, 325. So find tangent plane. At 2, 3, 5. And you'll notice that, right, when you plug in these numbers, right, 2, 3, and 5, so x squared, right, 4 squared plus 3, that's 9 times 4 is 36. So 16 plus 30. Are they serious here? 325. 325. 3, 2, 5. So x equal to 3 gives you 9. 2, 4 times 4 is 16, which is equal to 25, which is the square root of 5. Okay, so find the tangent plane at 3, 2, 5. So here you can solve for z. Z would be equal to the square root x squared plus 4y squared. Okay, so partial derivative of z with respect to x, right? So this is x squared plus 4y squared to the 1/2 power. So partial derivative with respect to x is 1/2 x squared plus 4y squared to the negative 1/2 power times the derivative of the inside, which is 2x. And the 2's go away. So we're left with x over square root x squared plus 4y squared. So that's cx. Zy is going to be very similar to that. 1/2 x squared plus 4y squared, and the negative 1/2 times the derivative of the inside, which is 8y. The half and the 8 leave a 4. So zy is equal to 4y over square root x squared plus 4y squared. Yeah. So z, the partial derivative of z with respect to x at the point of tangency, 3, 2, xy equal to 3, 2, is equal to, well, x is 3, and then this quantity down here is going to be 5 again. And zy at 3, 2, so at y equal to 2, this is 8, and on the bottom here you're going to have 5 again. So the tangent plane is equal to z minus the z coordinate, 5, is equal to 3/5 x minus 3 plus 8/5 y minus 2. Like that. So that's the, that's the sort of point slope form of the tangent plane. If you wanted to, you could put it in a standard form, right? So in a standard form, it would look like this. It would be 3/5 x plus 8/5 y minus z is equal to, so 9/5 plus 16/5 minus 5, right? So these get moved over there, the z gets moved over here. So it would be 3/5 x plus 8/5 y minus 1 is equal to, it's 25/5 over 5, it's 5, 0, right? So this one actually goes through the origin. So, and then, this tells us that a normal vector to the surface is 3/5, 8/5, -1. Right, which is actually equal to partial of z with respect to x, partial of z with respect to y, minus 1. More generally. Right, so that tangent plane equation, it gives you a lot, information about this tangent space, this tangent plane space, and also about this perpendicular line to the surface. So you have a tangent plane and a normal or perpendicular line. And that'll be important later in the last chapter. All right, 176. That was 176. 183. Oh, well, it's 8:45. All right, so